This is October-November 2023, paper 4-2, ATP to short. Okay, so question number, you will notice in every ATP that he will clear his motive, what he wants to do in this paper. He wants to investigate in question number 1, the spring constant of by two different methods. So by method 1, he will measure the spring constant, and there will be method 2, he will measure the spring constant again, and then compare the results and the that is what I'm expecting is going to happen in this question. So it says there's a method 1 in which the student measures. Of course, I've arranged the paper in such a way that I can clarify how to place the ruler for the accurate reading. So he wants you to measure or note down the readings up to 0.1 centimeters. So the accuracy is supposed to be 0.1. Now, he mentions do not include the loops at the end of the spring. What are those loops? These are those loops that he's talking about. These are not included in the instrument's reading. And he's also given these dotted lines, if you see clearly, what measurement he's expecting. Now, I would recommend that you use a transparent ruler and just superimpose the image of the ruler over these dotted lines, and so that you can see a dotted line underneath the ruler as well. The other thing that you need to keep in mind is that don't use the zero end of the ruler. Don't start your readings from there. It's recommended to start from a non-zero value. Okay, so I'm starting from, let's say, a digit 5. It goes up to 12. For the sake of example, of course, these diagrams are not accurate to scale. So whatever reading you get should be the true answer. Also, one more point, that if you try to attempt this paper by printing this out by a printer, or let's say you get the past papers from the market, it's very likely that they have changed the scale of the image to suit the size of the paper that they are using. So very unlikely that you will match the reading of the marking scheme. But the thing that you need to make sure is that the readings, or that the method that you're taking the readings of, should be accurate. If that's accurate, your answers will come out as accurate as well on the examination day. So no need to worry about that. Okay, so I'm going to copy the answer of the marking scheme, which is actually 5.5 centimeters. Okay. All right. Then he says the student attaches the spring to a clamp on a stand, suspends 300 grams again. And the diagram looks something like this. This experiment is exactly the same as we do in the Hooke's law chapter, or in the deformation chapter, to find the spring constant. He says now the length is 17.6. Use the equation this. Now notice in P4 or ATP question, he will always mention an equation that you want to use. He will not test your physics knowledge in terms of formulas. He will give you the formulas himself. So what is L1? L1 is given 17. What was L0? So go back. We see that L0 variable is used for 5.5. So 17.6 minus 5.5, you don't need to show the readings or the working over here. You just need to write down the answer because of 1 mark part. So this is going to be 12.1. Even if you do a little bit of working over there to note down the readings and use the calculator, that's also fine. Calculate the spring constant K1 of the spring. He, again, as I mentioned before, he will give you the formula himself. 300 divided by E. Where is E? E is found in the previous part. So 300 divided by 12.1 gives us an answer of 24.8. Sorry, this is 24.79 on the calculator. So up to 3 significant figures, we will write down 24.8. Okay, so notice that there are 3 significant figures of this number, 3 significant figures of this number. So the data actually controls what is the final number of significant figure. And if you are unable to figure that out, you can go forward with 2 significant figures, but primarily check for this rule. Okay, so it is supported to avoid the parallax error. Okay, fine. He says, according to you, what is the parallax error? Explain this, and how do you correct this? So in explanation, you can write down that this is actually the incorrect positioning of the eye, right? You're not looking directly at the scale. You're not looking at the scale directly in front of the scale somehow. Okay, so mention it in this way. And the very common answer for how to avoid this is to keep the line of sight perpendicular. You have to write down the word perpendicular to the scale of the ruler or the scale of the measuring instrument. Okay. Now, again, notice that he has carried out experiment for method 1. He's carrying out the same experiment by another method, which is method number 2, to do the same thing, right? So he says that he pulls the 300 grams and mass downwards by a small distance, and it starts oscillating. And there is a time T1 for 20 oscillations. This is the time T1 for 20 oscillations. He says, write this down or note this down up to 1 decimal place in the table. Now, even if he hadn't mentioned this one decimal place, how would you know that you have to do this with up to one decimal place? Because the next reading for time, or the reading for time of another experiment, is also up to one decimal place. So that gives you the idea that our readings should be up to one decimal place. Then you want to calculate the mean time. Of course, he's going to discuss these parts in the incoming parts, but I'm going to do this over here. The mean time, that would be calculated by 13.6 plus 13.8 whole divided by 2. So you will see that this answer comes out as 13.7. So again, this will be 13.7. There may be more decimal places, but keeping in line with the same number of significant figures, we are going to carry forward this idea. Now the period t, what is period t? So period t is actually for one oscillation. So how many oscillations are there? There are 20 oscillations. So this will be 13.7 divided by 20. This value comes out as 0.685. Now notice that since you're dealing with three significant figure numbers, your answer can be in three significant figures. It's your choice, completely fine, it's okay. So we can write down 0.685, or you can write down it up to two significant figures, which will also be considered correct. Again, as I mentioned before, if you're confused about the rule, you should always go back to the two significant figure rule. So I'm choosing this as 0.69, okay? And then you take the square of this to get the value of this table, and this will be 0.4761, which I'm rounding off to 0.48, right? Okay. Then he asks you to use this formula to calculate the K2. So simply 11.8 divided by 0.48. This gives us an answer of 24.6 newtons per meter. So this will be 24.6. Explain why the value of, now this is an interesting part, is obtained for 20 oscillations and not for one oscillation 2 times. Why can't we do this experiment just once? For example, a student starts the stopwatch at this point, pendulum goes here, pendulum comes back, and then stops the stopwatch. And then repeats this experiment 2 times. So he effectively has measured time for one oscillation. Let's say the time for one oscillation comes out according to the table. Let's pick out a value. For one oscillation is 0.69. Let's round it off to 0.7. So at one time, he gets an answer of 0.7. At another time, he gets an answer of 0.71. Let's say this is 72 seconds. Okay. So if he wanted to take the time for one oscillation, he would take the average, and let's say he lands on the final time for oscillation as 0.71 seconds, for the sake of example, of course, right? Now notice that there is a problem. The problem is that the human reaction error while starting and again by stopping, or while stopping the stopwatch, is around 0.3 to 0.5, depending upon the alertness of the person who's conducting the experiment. So it means that there is a chance that this number is actually either overestimated or underestimated by this number of time. So there is already a very big error in this reading, right? Because you're measuring it for one oscillation. So it's very likely that you did 0.3 seconds too soon, or you clicked it 0.3 seconds too late. Okay, so other than that, or in contrary, if there is a student who measures for 20 seconds or 20 oscillations, then the time he got for 20 oscillations, let's say, is 13.7 seconds. How many times is this student committing the error? So one time starting the stopwatch and one time stopping the stopwatch. We're taking the absolute worst. So when you divide this number with 20, the answer or the significance of starting and ending human reaction error will decrease to a very, very small number. But over here, since you are just taking for one oscillation, if you divide this with 1, the significance of the human reaction error stays as it is. So 0.3 seconds to start it and then 0.3 seconds to stop it. So that's a very big error. And notice that the time for one oscillation is 0.7 seconds and the human reaction error to start and stop it is 0.6. So what is the true value? Did you actually measure the oscillation for pendulum? So the whole experiment goes into question, right? But over here, on the contrary, if you do this for 20 oscillations, even if there is a human reaction error of, let's say, 0.6 seconds, let's write them separately. 0.13.7 plus 0.6 seconds of error divided by 20. Now this will be divided by 20. This will also be divided by 20. So the error is being divided by 20. It's being spread out because of the average, which means its significance will decrease and we will get closer and closer to the true value. Now, some students might argue, if this is such a good practice, then can we take it up to, let's say, 40 oscillations? Can we go up to 100 oscillations? Yes, it sounds good, and effectively, mathematically speaking, it will improve the results. But the problem is that when you do this experiment in the laboratory, you'll notice that after approximately about 20 oscillations, no matter how big, small, or whatever the length of the pendulum is, the oscillations start decreasing and they become too slow for time to be calculated. Although the speed of the pendulum does not control the time period as well, you will learn this in A levels, but at the end of the day, we have universally accepted in the science world that 20 oscillations seems like a good number. It's a balance between both, right? So what can we write down, and how, whatever I've discussed, how can we narrow this down into theory? What can we say about this? So this actually reduces human reaction error as the error gets divided by the number of oscillations, right? Okay. Moving on to question number 2. Again, read the first statement very closely. He will mention what he wants to do in the experiment so that you can make up your mind what you're supposed to think and what you're not supposed to think. He says he wants to investigate the rate of cooling of water. So it's something related to thermometers, rate of cooling, room temperature, something like this. Now, he was working with a hot water tub. Okay, so the room temperature is 22.5, something to note down. He pours in 200 cm3 of water, and then he makes sure that the bulb is on the top side of the beaker. Okay, then he waits for 30 seconds, starts a stopwatch, and then reads the thermometer. Notice he's waiting for 30 seconds before taking the reading. Okay, so the first test is to read the scale. Now he wants you to write this down out to 0.5 degrees centigrade. So if you zoom in, I'm zooming it in. So if you zoom in, notice which scale is representing what. Be very careful while counting this. So starting with 80 and we're going at 90, that means that these scales are representing 1 degree centigrade. So at the center, quickly, I can see that this is 85. But this line that I'm representing, or this line that I'm seeing over here, this line that we're seeing is 86. But is this 86 or is this 85? If you zoom in further, you will realize that this is somewhere in the center. So this means that this should be 85.5. Okay. Okay, so now let's zoom out. So the value is 85.5. So I will go back to the table and I will write down 85.5. Now, notice that this experiment is when the bulb is at the top of the beaker. Let's say this is the beaker, this is the liquid surface, this is the bulb location. And the second set of readings on the other side is when the bulb is at the lower side of the beaker over here, right? It is just above the bottom. So this is one of the confusions that you might experience while solving this ATP on a quick glance, right? He says, explain why the student wait for 30 seconds. An excellent question. We need to allow the thermometer to respond, to react to the change in temperature or the hot environment that it is being placed in. We need the liquid inside the thermometer to respond, to absorb thermal energy, reach a thermal equilibrium, and then tell us the true value. It's not possible that we immediately put in the thermometer, we take it out, or we just let it stay there and note the reading immediately. We can't do that. Okay, so why are we doing this? So that we can allow the thermometer to absorb thermal energy, expand the liquid inside, or let the liquid inside the thermometer expand, okay? And so it can respond to the change in temperature and eventually, or by reaching a thermal equilibrium between the liquid and the thermometer, okay? Only then we can do that. So the 30-second gap or 30-second pause is for that purpose. The student waits for 3 minutes, reads the thermometer, record the new temperature. So he's waiting for 3 minutes, as we can see in the table as well, okay? And now he places it to the lower part. This is what I've explained earlier, that one experiment will be carried when it is at the lower part, one experiment will be carried when it is at the top part. So he says use this equation to give the answer. Up to 2 significant figures he's mentioning himself. So first we have 85.5 minus 78. So 85.5 minus 78 divided by 3 minutes. You notice he has given the unit. It means that some students would most likely may convert this time into seconds and get a different answer. Even for those, they will be using two significant figures. So the answer of this comes out as 2.5 degrees centigrade per minute. I'm not converting the minute into seconds. It's extra work and with no extra credit. So no point wasting time. So this will be 2.5 degrees centigrade per minute will be good enough. Okay, question number 2, he says, use table 2.1, page 7 to calculate PB of the hot water at the bottom. So we want to do this again, but for this data set. So this is 86 minus 77. So 86 minus 77 divided by 3. When you do that, your answer is going to come out as 3 degrees centigrade per minute. Now, please notice he's mentioned that this should be in two significant figures in the previous part, that all of these parts will be in two significant figures. So we can't write down 3.0. We can't write down 3. To make it two significant figures, I will add a 3.0 over here. So degrees centigrade per minute. Use your answer in B1 and B2 to suggest why hot liquid should be stirred before measuring its temperature. Now notice that the top part of the container is losing temperature at a different rate, and the lower part of the thermometer or the beaker is losing temperature at a different rate. But there is a non-uniform loss of thermal energy, which means that this will introduce inaccuracies in the future measurements that we're going to take. So what would be the best practice? The best practice is to stir the liquid, right? So how do we justify this? We'll write down that we are doing this to ensure that whole liquid or complete liquid will have or can have the same temperature, right? State one way in which the apparatus in the experiment is arranged to make it easy to read the thermometer. So we can go back, look at the apparatus again, try to see from a practical standpoint, what changes can you do? So it's already in a clamp and a stand, right? It's already held in place. What can you do? So you can rotate the thermometer in such a way so that wherever you're standing, your eyes can directly look at it. Okay. So again, one of the changes, you can go to the marking scheme and memorize the rest of the answers, because this question is a repeated question. Okay. So rotate the thermometer so the scale is facing the student. Okay. The experiment is being repeated to check the results. Okay, fine. Suggest one variable that must be kept constant. So a very common question, you need to make sure that it is the same volume, it has the same mass, right? It has the same starting temperature. Okay. So all of these are control variables of the control of these experiments. The student leaves the thermometer in the hot water and waits for 30 minutes. 30 minutes is a very long time. He's exaggerating the situation deliberately so that he wants to see whether you pick this information up or not. Or are you able to decipher this or not? So why is he waiting for so long? Because when you do wait for so long, what's going to happen? When you bring a cup of tea in your room and you wait for a very long time, what happens to the cup of tea? It gets cold. And it reaches or gets the same temperature as the room by achieving, or at that stage, we call that thermal equilibrium. So at this point, the cup of water will also have the room temperature, which is 22.5. So don't need to predict this. This is actually an answer we already know. So this is 22.5. It will be at room temperature. And notice that this is a repeated question. This whole question is a repeated question. And please be advised that this question number 2 can be asked as a question number 4, which is the new question introduced in your syllabus, or the new type of question, in which you have to write down method of analysis, in which you have to write down how to conduct an experiment. So the whole past paper of ATP from now on, every question 1, 2, and 3 is a method that you can memorize for future question number 4s. Please keep that in mind. Now, question number 3, he says he wants to investigate how potential difference across the terminal of the power supply. He wants to check the power supply changes as the current in the circuit changes. Okay, fine. So he says this is the reading of the voltmeter that he's measured, right? Sorry, I think we need to go back. Yes, it's the same. Okay, so question number 3. So what's the reading of the thermometer at this point, of the voltmeter? Be very careful. This is to this is 3, and this is 2.5, which means that this is going to be 2.9. So this is actually 2.9 volts. No need to write in the units. It's already given. The student then connects the crocodile clips and does these following experiments, and then opens the switch. Okay, so this is the reading at that point. So this is 0.1, 0.2, 0.3, and this is 0.5. So this should be 0.31. You can zoom in and see what's what. So this will be 0.31. The student closes the switch, repeats the value from D80 to D20, and this is the result that he gets. First and foremost, write down the value so that you can refer to this again and again in the table in the next question. Okay, so the distance was being measured in centimeters. You can go back and refer to the scale. So slash centimeter, slash voltage as volt, and slash current as ampere. Okay. And then he mentions that you need to draw a graph using these coordinates. So I've taken this graph, placed into another image, and I've drawn the graph for you. Now notice that I've color coded these codes as well, which coordinate represents which place, which location. But first, how do we select the scale? You see, very easy way to do this would be to just count the number of spaces. How many spaces do you have? So you have 1, 2, 3, 4, 5, 6, 7. So you have 7 spaces along the y-axis. He says that voltage is going to be on the y-axis and current is on the x-axis. So I have 7 spaces, right? What's the largest number I need to represent? That's 2.3. So 2.3 divided by 7 gives me an answer of 0.33. 0.33. So I have to choose a number larger than this, but a convenient number. So I could choose 0.4, but I am choosing 0.5 as this is easier to count mentally than 0.4. Again, you could have done this with 0.4, no issues in that. That's also a convenient scale. It's your choice. Then for x-axis, what's the largest number? The largest number is 0.88. So 0.88 divided by how many spaces are available on the x-axis. So 1, 2, 3, 4, 5, 6, 7. This also comes out as 7. Now, when you calculate this, you're going to get answer as 0.125. Now, 125 is not a convenient scale. Even 1.3 is not a convenient scale. 1.4 is also not a convenient scale. So you can choose 0.15, but the problem is that when you do it this way, you will get odd numbers in the scale. Nothing wrong with that. You can choose this scale as well. But again, mentally, for me, calculating a scale of 0.2 is much easier. Although there is a trade-off. The trade-off is when you choose 0.2, your graph shrinks to a very small sample size. If you choose 0.15, it will be much spread out, which will increase the accuracy of the results. But then again, in the favor of mental calculations, in the favor of saving time, I have selected 0.20. You can do this with 0.4 and 0.15 and compare the results. Do you get the same answers as the marking scheme, or do you get different answers? Anyways, so that is how you choose the scale. Okay, you choose and make this decision. So I've used the same scale on y-axis and x-axis and drawn it accordingly on the graph. What you can do is, I'm going to pause the video at this point. You can pause the video and observe how the graph is drawn, how the coordinates are drawn first. I've color coded them as well. Okay. So you will see the red coordinate over here, the orange one over here, the green one over here, blue one over here, and the purple one somewhere along this line, right? Okay. And once you've once you're done placing the, okay, so one more thing, how to place the coordinate. Let me zoom in and tell you what's a wrong coordinate placed and what's the correct coordinate, what the Cambridge considers to be correct coordinate. You see, if this is the box that you're dealing with, if you fill in this box by your lead pencil, this is wrong. If you fill in half the box, this is wrong. The accurate or the most accurate coordinate would just take half a space off the box in terms of surface area. This would be a coordinate on the line. This would be a coordinate over here. Let's say you want to draw a coordinate at this point. It should be not bigger than this. Yes, what you will do at the end to show the examiner that you've drawn these coordinates accurately. Once you've done the coordinates, once you've plotted them like this, you've drawn the line of best fit, you've done your job. At the end of the experiment, at the end of making the graph, now what do I mean by at the end of the day? You see, first you draw the graph, or you draw the coordinates, then you draw the line of best fit. And for the line of best fit, the number of points above the line and below the line should be the same. The first try is to take the maximum coordinates on the line. If you are unable to do that, then match the number of points above and below the line to be equal. So over here, you can notice that the green coordinate and the blue one are below the line. The orange one and the purple one are above the line, and the red coordinate is actually on the line. So whatever coordinate comes on the line is not participating in the line of best fit race anymore. So now you have to just balance the points. Okay, so best fit line is drawn, coordinates are drawn. Most likely he will ask you about the coordinates, and most likely he will ask you about the y-intercept or the x-intercept. This is a common occurrence in these questions. So students, what they do generally is that they start the line from this location and end it somewhere over here because the coordinates are covered. If by any chance he's going to ask you about the y-intercept, what would you do then? You will come back and draw the line again, which is going to be an incorrect way of approaching the question. My general recommendation is always draw maximum length line to cover the complete graph. If the question is asked, go from x-axis to y-axis or go from x-axis to y-axis. Go to the extremes so that if the question arises, you don't have to draw it again. You don't have to come back again. Okay. All right. So based on these ideas, I will pick my coordinates beforehand, and yes, you are required to draw this triangle, but due to the limitation of tools I've drawn solid lines. You are not required to draw solid lines. You can draw this dotted lines as well to highlight the coordinates that you've selected. Triangle of gradient is necessary. You will lose a mark if you don't draw this. Then at the end of the question, when you've done all your working, just to tell the examiner, because your coordinate is very small, where are those coordinates? What will you do? You will encircle your points on the line where you've drawn those coordinates so that the examiner knows where those coordinates are. So the examiner can pinpoint and look very closely where you've taken those coordinates from. Okay, so that is how you draw the graph. This is what best fit line of best fit means. This is how you draw it. I've color coded the coordinates as well. Okay, and I've picked out the coordinates of the gradient as well. Okay, moving on. He says calculate the gradient as usual. As I mentioned before, I was expecting this. So it will be again y2 minus y1 over x2 minus x1. So this is 0.55 minus 2.60 divided by 1.20 minus 0.18. Another thing to keep in mind is that how much distance should there be between the coordinates. You see, the coordinates should be so far apart that at least 50% of the length of the line is being covered. Don't choose coordinates that are very close to each other. That is wrong. Don't choose coordinates that are taken from the graph. Don't do that. That's also incorrect. So the only best practice is to go as far back as possible along this side and go as far as possible on this side and pick out the coordinates that are exactly on the lines. You don't have to guess them. Okay. All right. So when you calculate this, this is going to come out as 2.00 something. So up to two significant figures, I will choose 2. Plus he says that M is actually equal to resistance. So I will add a unit of ohms over here. Okay. The intercept between y-axis and V0 is again a voltage V. So again, notice that he's asking you about the intercept of the y. So that is why I was emphasizing that always draw the maximum possible line that cuts all the axes that are possible to avoid this in the future. Because I generally suspect that this is going to be a part of the question. That's why I recommend doing it this way. Now, when you zoom in and check this box, this is actually 2.90. Now, I will write this down as 2.9 voltage, 2.9 volts. He says compare the value of V down. Luckily, my value of 2.9 of the current experiment and the 2.9 of the starting experiment are exactly the same. There is no error, but for the sake of solving the question, I have to solve it. How do you deal with this question? This is also a question from A-levels. You will encounter this in A-levels as well. But how do you deal with this? What is he trying to do? Notice that we have two values of V0. We have V0 from part A, which is 2.9. We have V0 from the recent part, which also has a value of 2.9. For the sake of example, let's say that this is 2.8, or my value came out as 2.8. What is this 10% error? I want to confirm that whether these values are within 10% of each other or not. Do they fall in the same range or not? How do you do that? Pick any value you want. I generally pick out the largest value because that gives me the largest range so that I can generally say yes to the accuracy questions. But that is again my preference. There is no reason behind this. You can choose 2.8 and perfectly solve the question the same way as well. Now let's choose 2.9. What is 10% of 2.9? So 2.9 multiplied by 10 divided by 100, or 10%. This is equal to 0.29. What does this mean? It means that there is a possibility that the answer that you've calculated is at least 10% more or 10% less. So to compensate for this, what I'm going to do is I'm going to add this number plus 0.29 and then subtract this number minus 0.29. The same thing, okay? I will do this for both of them. Now, when I do that, the addition answer goes to 3.19 and the subtraction answer goes to 2.61 volts, which is a very large range. Okay. Now, my duty is that if I use this calculation for the range, now I need to check whether this number falls in this category or not. Does it fall in this range? Is 2.8 between this range or not? Yes, it is. So the statement or the calculation is going to go this way, the one that I've done over here. The statement would be yes, they are within 10% of experimental error or 10% accuracy, or they are within the limits of experimental accuracy of each other. Luckily, in my case, my answer was 2.9, even in the second method, the graphical method, which means that I will perform this calculation and I will give the same conclusion that the 2.9 does fall in this category. So yes, my statement will be yes, that this is within the 10% limit of experimental accuracy. Or you can say that the experiment conducted is within the 10% limit of experimental accuracy. So whatever we have done as scientists, as engineers, as physicists, we have done this as accurately as possible. Question number part G. He says, suggest one practical problem that why we can't go less than 20 centimeters. If you go back to the graph to see the trend, you will see that if you go less than 20 centimeters, the voltage, right? Sorry, you have to go back to the table. If you go less than 20 centimeters over here, if you go less than 20 centimeters, notice what's the value of the current. The value of current increases to a very large value. So what problem will it cause? It can cause two problems. The first problem will be very simple and straightforward. It will cause a short circuit. And short circuit is a condition when there is minimum or no resistance available in the circuit and the whole voltage is utilized to cause a very high flow of current. Otherwise, it can heat up the wires, or wires can become hot, or even melt the wires, which is of course an unsafe condition. Part H says to draw the same diagram but using a variable resistor. So first let's complete the circuit implementing a variable resistor. This is the symbol for a variable resistor. Let's complete the diagram. I would advise you to use a ruler and a lead pencil to draw these diagrams. Don't draw them freehand. And we will connect the voltmeter as it is, as given in the question at the very beginning. If there was any confusion, this is how the voltmeter is going to go. Because checking the voltage of the power supply. So we still need to check the voltage of the power supply by changing the resistance of the circuit. Okay, all right. Question number 4 again. This is the question that is introduced. You can say not introduced, but it's not new. We have experienced these questions previously in the past papers as well, but now he has explicitly added this question as a part of your ATP, and it will be a part of every ATP from now onwards. From 2023 onwards, it will be a part of every ATP. That is a design and planning question. Now, again, this is what this question or this setup is actually one of the repeated questions. What he wants to do, he wants to investigate the average speed of the trolley moving along the horizontal bench. So he wants to find out the speed of the system. All right. Okay. So what's what? The stopping distance, he defines what stopping distance is going to be, and he defines and he asks you to plan an experiment, okay, along the bench. This is the bench, okay, all right, until it comes to rest depending upon its mass. Again, depends upon its mass. So the masses given in the diagram will be changed or will be used in the question to observe what difference does that make by increasing the mass. Is a heavier car difficult to stop, or is a lighter car difficult to stop? This is what he wants to find out. So he also gives you the formula of the average speed, the stopping distance, and the time. Where is the stopping distance? The stopping distance is mentioned in the question. Where will you find it? Where is the stopping distance going to be considered for? Okay. Then my basic formula for this question for every student is that the question is for 6 marks, right? Even if you turn a blind eye towards the experiment, you don't know anything, at least cover these 4 points he's mentioned. In any order, in any sequence, he will give you at least some marks for doing this. Don't leave this question out. He's giving you clear instruction what he wants you to find out. He wants you to explain briefly how to carry out the investigation, stating any of the apparatus needed. What will you do? How will you carry out the experiment? So you will release the trolley from a point, right? And start the stopwatch when it leaves the ramp and stop the stopwatch when it actually stops moving. This is what you're trying to do, right? So you carry out or you write this down in a statement form to write down the first point. The second point he mentions is there any extra apparatus you need? Yes, we need. Yes, we need an extra apparatus. We need a measuring tape or a meter rule, depending upon the situation. We need a stopwatch to measure time, right? So these are the things that we require. So we are covering, or we have covered successfully point number 1. Okay. Then he says, what do you want to keep constant? What will you do in the experiment so that it does not affect the rest of the experiment? So we are changing the masses. We can't keep the masses constant, but what we can keep constant is the height of the ramp, the starting point where the trolley is being released from. Mark this on the stand and then make sure that if it is being referred with the previous or the back wheel or the front wheel, and then move ahead with the question, right? Okay. So these will be the key variables to be kept constant. Then draw a table. Now this is important. What do you do with drawing the table, right? One more thing, that if you are doing this experiment, then adding the mass and then conducting the experiment one time is not enough. It will be a good idea to repeat the experiment and then take the average of those results. That is also an added benefit. This is a part that is, or this is the answer that is going to be followed in every question of question number 4. Okay, and then of course keep on adding mass or keep on removing mass, whatever way you're setting up the experiment for yourself. Then when it's about setting up the table, be advised, he's mentioning that you're not required to add any values. You don't need to add values. What you need to add is what you're measuring. What are the variables that you're checking? So what are you changing? You're changing mass, which is being represented in grams, right? What are you measuring as a result of this? You're measuring the result of distance traveled, or the stopping distance, and you're measuring the time it took to do that. So this will be measured in seconds. Now, why I have arranged them in this way? This is for A levels, of course, not for O levels. When you go to A levels, it's a good idea to arrange the data in such a way that it is easy to visualize. Now, see, if you calculate the average speed, you will need the distance divided by time. So you need this value, let's say call this X, divide this with Y. This is what you want to do. So to me, at least as a student, dividing this number with this number will be much easier if I write them the other way around. You see, if I write time first and distance later, it's not going to be wrong. If you write this over here and write this over here, it's not wrong. But again, as a scientist, as a physicist, it's easy for me to visualize that this number comes first and this number comes later. So that makes your life a bit easier. So this is how you set up the table. And of course, please use a ruler and please make columns for this table. It should look like a table at least. Then the last part, which is very important. He says, once you've collected the readings, what are you going to do with the readings? What are you going to do with the readings? What can you do with the readings? So there is a hint present in the question paper. What do you do when you take the readings? You draw a graph. And when you draw a graph, you can predict results that you have not even measured, that you've not even taken. For example, have we taken or have we done the experiment at this point? No, we've done an experiment at this point, we've done an experiment at this point, but I can very well predict what will be the value without conducting the experiment. So whenever we gather values from real life, let's say we plot or we populate a table. The end goal is to draw a graph. Okay, so you will also mention that we will draw a graph, okay, for different masses. So this is going to be, let's say, distance divided by time. Let's say this line can be for mass m1. Let's say this is the mass m1. This is mass m2. This could be the line for m2. This could be line for m3. So by looking at the gradient of distance time graph, we can conclude regarding the speed or the average speed of the trolley. Okay. One more thing, you can also suggest as a conclusion based on your own observation that the higher mass will be taking the longer time and would of course have a higher average speed. So always mention drawing a graph, but always mention what is going to be in the y-axis, what's going to be in the x-axis. A simpler way of doing this in English would be you will say that plot a graph or plot a distance/time graph. It is understood that if you write distance first, this will be on the y-axis and this will be on the x-axis. That is how you write this down in English. And then mention something about the gradient, that they can have different gradients. The highest gradient will be the highest speed and it will be the highest mass, or it will be of the trolley that has the highest mass. So that is how you draw the conclusion on this common observation. All right. I hope that we understand this, how to tackle, how to deal with the NATP question or ATP paper.